to... Oh, hi. I didn't see you there. Hello, everyone. I was just brushing up on some of the vocab in the next set of notes, and properties of similar triangles. Upon an angle bisector of a triangle, divide the opposite sides into two transversal parallel two sides of a triangle the other two. Hang on! We'll get it all cleared up in this set of notes. Let's get started. So in this set of notes, we're going to focus on triangles, properties of similar triangles, particularly ones that are self-similar using parallel lines. This set of notes will look a little bit different in structure because I'm going to be jumping back and forth from the definitions page to the 3 examples that we'll do throughout the slides. So let's take a look. So for our first example here, we'll be looking at what the Triangle Proportionality Theorem does. For starters, it states if a line parallel to a side of a triangle intersects the other two sides, then the triangles are similar. And the converse also applies. Well, what's this mean? For starters, you need to have a triangle, and that triangle needs to have a line drawn into it that is parallel to one of the other sides. So if I mark this diagram here with the parallel lines, this image kind of represents the triangle proportionality theorem. So let's see what it means to try and solve a problem with it. Here is a problem which our triangle proportionality theorem will be helpful. It says to solve for a length AB, which seems fairly straightforward since we have a length AB right here. But in order to solve for that, we need to know, first off, that these two triangles, AED and ACB, are similar, and also how to set up a proportion between the sides that are listed. So, for example, I need to solve for AB. So I'm going to put AB there. But what can I compare AB to? Well, at least for now, I'm going to compare it to AD, a smaller version of AB. Well, I don't know what either AB or AD are, so I have to create another proportion that compares sides I do know. So if I have AB as the longest side here, what can I compare that to, also in the triangle, as a side that I know? I'm going to have to go with AC, since I know that is 8. And I will use that 8 in setting up this side. And since I used AD here, the comparable side would be AE, or 3. Now I do have to go back to AB and AD here because I should be using the x variables in this expression. So for AB, I am using the x plus 3 and x minus 2, which overall will be 2x plus 1. Then AD will be just the x minus 2 here. So after cross multiplying, I end up with 6x plus 3 and 8x minus, well, that's not 2. There's a mistake here. I need to fix this 2 since it's going to multiply by the 8. It should actually be 16. There, now I fixed it. Now I've cross multiplied. And with that, I can finish this solving. I can subtract 6x from both sides, and I can add 16 to both sides. So I'll have 2x here, and I'll have 19 here. Which is all well and good, and it's helpful, since I'm trying to find out... Well, hang on. I'm not trying to find out what x is. I'm trying to find out what AB is. AB is up here. This is AB, the original value, 2x plus 1. Well, if 2x plus 1 is what I'm looking for, but I have 2x here, I mean, I could just say 19 is 2x plus 1. AB should be 20. 20 is our final answer for the length of AB. That's what an example of the triangle proportionality theorem looks like. The second definition we're going to be looking at here is two transversal proportionality. This is if you have two parallel lines intersected by transversals, and those transversals are all proportional. It's going to be helpful to draw a picture here. Suppose we have some parallel lines, and we're going to draw some transversals between them. When we do, these transversals all fit proportionally to each other. And I think this is another example which will require another example. Notice here that we're just trying to complete a proportion, And in order to do that, we need to know what side lengths we're comparing. First off, we've got AC compared to DF. And you'll see here that those that I've highlighted here with red are proportional, although they're not equal. So the fraction built up here needs to be equal to the other fraction here. Well, what side can I compare it with if I'm trying to match it up with DE? Well, if you look, DE is here, so the side that I should naturally be comparing it to is AB. And this proportionality is used to solve problems related to transversal proportionality. My answer to this question is AB. If I was presented with some variables to solve for here, I would simply be replacing the segments with the measures they give us in order to solve. Our third theorem is going to require that I get out of the way. So we're going to hide me for a moment. Our third theorem here is the triangle angle bisector theorem. This one is arguably the most complex. It took me a longer time to learn this one. But the rule is, if you have an angle bisector inside of a triangle, then the remaining sides should be proportional to each other. Let's take a look at an example to see what this means. So, how does this work? In our example here, we're going to use that the angle is bisected in order to solve for a missing length here, x, with the proportional side lengths that are created in these two smaller triangles. What's the proportion that's been made here? Well, it would be AB goes with BC and AD goes with DC. This proportion is created because of the angle bisector. If we replace these segments with the lengths, we'll be able to solve for the missing length. There, with the sides replaced, I can cross multiply, divide, and get to my final result. 5x equals 42, which means x is 8.4. Putting in the 8.4 in for x actually finishes the problem. So I'll wrap up this set of notes with one more little quick recap. We've seen some different versions, different types of scenarios that would create triangle proportionality or segment proportionality within triangles. And so let's see what that would look like in each of these three cases. For example, in this first one, what proportion could I build from this image? There are a few proportions you could make, but I would argue that this one is the cleanest. It goes from A to the longer segment A plus C, and B to the longer segment B plus D. How about this one? What proportion can we build out of this image? This one's a lot more clear-cut. I would claim that one of the proportions you can create out of this image is A over B equals C over D. Finally, what could we do over here with this one? The most straightforward proportion we can make out of this one is A over B equals C over D. Again, the mirroring the kind of look that we have for the proportion in the previous one. That about wraps up this video. Here we've seen some examples about self-similar triangles and proportionality, particularly with parallel lines, or in the latter case here, with a angle bisector. Stay healthy and safe. I wish you the best of luck. Bye now.